Hi, everyone. Uh, this video will serve as an introduction to our energy topic, which will follow the centripetal force and gravitational forces topic. Don't let that lead you to believe that we're done with forces, though. Force is a integral part of energy. Um, to start off, I'd like you to just sit and think about what these words on screen mean to you. Uh, Work, energy, and power. Think about if you were to write a definition yourself, what it means to do work or what work is. I want you to think about what energy is or what energy can do, maybe different types of energy. And I want you to also think about what the definition of power is. How does power, or rather, what is power and how does it relate to these other two words? So just think about that for a second. You do have these three words plus many more in your term maps, of course. So if you don't have those open, and you are in the habit of adding information to your term maps as we talk about them in class, you could open those now for sure. I imagine many of us would agree that work is some type of action. Things are happening when work is done. Um, you know, Outside of a physical context, work is doing something, completing a task. In the context of physics, though, work is energy. Specifically, work is a change or transfer of energy. But then, what is energy if work is a change or transfer of it? Well, again, if you think just common sense, energy is what? That stuff you need to do something. It's some sort of reserve of some quantity that lets you take action. Well, if you ask a physics textbook, energy is the ability to do work. And so both of these words in their physical context are just saying, well, they're the other. Work is energy, energy is work. What is that really telling you? Not really much. Of course, this is physics, and we do have mathematical equations to also describe these concepts, and perhaps there some more meaning will be derived. But first, before I introduce you to any equations, there are a few more concepts I'd like to talk about, as well as what power is about. I haven't talked about that yet. I think we can all agree that power kind of makes you think in the same context as energy, and that is correct. Power is simply the rate of energy or work. And again, if power is the rate of doing work, it means it's related to either work or energy. Doesn't matter because work and energy are the exact same thing. But that word rate means that time is involved. So in an equation, power is simply work over time. But I'm not going to write down any equations yet. I'll save that for towards the end of this video. I mentioned that I did have another concept to introduce, and you can see that in the presentation I have within your classroom now for the new section of energy. One important thing to, I guess, take away from our introduction to energy is how it's measured, and that is in the joule, Joule. The abbreviation for the joule is a capital J as a unit. Now, kind of like many units we use in science, the unit of the joule is one that we are not too familiar with as a culture because we traditionally measure energy in calories. In fact, you can perhaps look at a nutrition label right now of a drink or a bag of snacks you might have nearby within arm's reach, and just take a look at one of those nutrition labels to see how many calories is in a serving of whatever consumable you're looking at. And I want you to take a careful look at the label that says that whatever number of calories against the word calorie I have in the presentation on screen. In my second bullet here, I'm telling you that 4.19 of these joules of energy is equal to 1 calorie. But look at that word calorie on the label versus the word calorie I have on screen. There's something different about them. You may not be able to see right now, but let me explain. And that's only because you're probably thinking it's insignificant, but on every nutrition label, the word calorie is always capitalized. That capital C actually translates to kilocalorie. And that's, of course, not the same thing as a regular calorie. So a capitalized C calorie really means 1,000 calories. So let's say you're looking at, a 100 calorie granola bar. Well, that's actually 100,000 calories as it should be measured. And that translates to, I suppose that would be about 4 million joules. Or sorry, 400,000 joules, since every calorie is actually over 4 joules of energy. Why do you think the nutrition labels label kilocalories in disguise by capitalizing the C? It's really no big secret. If I'm eating a granola bar and its label says it's 100,000 calories, that doesn't sound so good. I don't want to eat that. But hey, if we manipulate the unit of energy and translate it to kilocalories, oh, now the number's only 100. That doesn't sound so bad. It's just a marketing thing. All the same, we don't measure energy in calories. We measure energy in joules. There is a conversion on screen, although almost every time we will be given our energy in joules, so there's no need to convert. I have this pentagon of arrows in this picture. This is just an example of all the different types of energy we may have. There's mechanical energy, thermal energy, chemical energy, etc. Work is the process of changing from one type to another. And specifically, there are processes to allow that work to be done, that transfer from one to another. For example, if we have energy in a mechanical form and we allow friction to act, that could turn into thermal energy. To translate these words into ones that make even more common sense, mechanical energy is the energy of motion, while thermal energy is the energy of heat. Friction can take moving energy and turn it into heat. You can try that right now for yourself. You've got 2 hands, put them together, move them. Your hands are warmer. You've taken what originally was chemical energy from the food you ate, put it into mechanical energy. You have that energy to move your hands, and then that motion energy became thermal energy. That's a double transfer of energy just with this simple action. And remember, I'm going to keep saying it, the transfer of energy is also known as work. Both of those measurements are measured in joules. Before I click away from this screen and get into our first equation, I also want to be very clear about where the concept of energy came from. It's completely made up. There's no direct way to observe energy in like some pure form in reality. Energy is simply a mathematical concept that was made up in order to figure out measurements in a different way. You'll all see very soon that we can take an energy approach to some problems we've already done, especially with kinematics, and see that we can obtain the exact same answers of measurements, for example, maybe velocity or maybe distance from a purely energy perspective and energy equations, while we can take a look at kinematics, use completely different equations, but wind up with the exact same answer. But that's coming soon. One last idea I'll leave with you in this video is our first energy equation, and that is the work equation. You can see on your screen now, the work equation is here. It's also found in your reference tables. W is the variable for work, measured in joules. Work can also be described as the combination of a force acting across a distance or a displacement. So work equals F multiplied by D, D for displacement. But we have to be very careful when we use this equation. The displacement must always be parallel to the force acting. So parallel, same direction. If I'm applying a force on an object that is not acting in the same direction as its displacement, well then I can't just take those two numbers and multiply them together. I might have to do some trigonometry or geometry to make sure that the force and the displacement of the object are in the same direction. So if I push an object and it goes the same way I push it, all good. But if I'm pulling on an object at some angle and I make it move not in the exact direction I'm pulling it, I'm going to have to do some vector components perhaps. So just be careful. I can lift an object. I can lift this pen. I'm applying a force upward to do that. It moves upward. I'm doing work. I could do this. I'm not applying the force to make it move left and right. I'm holding it up against gravity. It's the friction in my hand that's actually allowing it to move left and right. As I move my hand, the pen stays with me. The pen stays with my hand because of friction, but I'm not responsible for that. So if I'm asking about the force that my arm is applying on the pen, that only deals with the up and down, left and right. That's not me. That's just a force that exists between the pen and my hand, friction. I don't control that. So just think about the parallel nature between force and displacement when we're dealing with work. And I just want to back up and point out that even though this is the mathematical equation for work, in the case of moving an object, it's the case in every energy transfer. Somehow or another, every time work is done or energy is transferred or changed, there are forces being applied across parallel distances. So that means if force is involved, that translates to masses being accelerated across displacements. That is the mathematical definition of work. And maybe that will make more sense than just saying, oh, it's a change or transfer of energy. What does that actually mean? It means, once again, that a force is acting across a displacement. Therefore, a mass is being accelerated across some displacement. There is a problem that I would like you to try before you officially end class today. It's not just watching this video, I'm afraid. If you can please open up your document. I have a very basic problem of a box being pushed with a force across a displacement. I would like you to solve that question as well as the question number 2, where we now have the force angled. So like I mentioned a few minutes ago, you'll need to break this force apart into components. Only the parallel piece of the force matters when it comes to the work calculation. Otherwise, you can use the modified equation that I have in the presentation. That being, you can take your force and displacement and take the cosine of the angle between them. That in itself is taking the force, splitting it down to the parallel piece of the force, and then that will solve for the question directly rather than trying to separately solve for the triangle of components. I'll leave it up to you which strategy you'd like to employ. Good luck. I'll see you guys tomorrow when we can further discuss energy and the equations associated with it. Bye-bye.